Hello and welcome to the last video in our three-part series on backpropagation. In this video, we will do backpropagation on the second equation. Let's get started. Now in the video for compute graph, we saw the slightly more complicated equation, y equals 5x squared divided by 1 plus e to the power x. And this is all the constituent intermediate variables that we got. The only change here that I've defined a new variable z5 equals 1 divided by z4, or the inverse of z4. And so y now becomes a product of two intermediate variables z2 and z5. Back in that video we had y equals z2 divided by z4, and I've simply replaced z4, 1 divided by z4 with z5. That's the only change you see here. And the corresponding change in the compute graph is z4 goes to this inverse operation, comes out as z5, and then we multiply it with z2 to give us y. Okay, so with that out of the way, let's do the backpropagation graph for this. So as usual, we start with the leaf nodes. So we replace y with dy dy. Let's go in this direction, replace this with the gradient of z2, which is dy dz2. Replace this with the gradient of z1, which is dz2 dz1. Replace x with the gradient of x, which is dz1 dx. Come back to y and replace z5 with the gradient of z5, which is dy dz5. Replace z4 with the gradient of z4, which is dz5 dz4. Replace z3 with the gradient of z3, which is dz4 dz3. And here, we've already replaced x with dz1 dx. So what do we replace x with? Well, we just accumulate the gradient from this path, which is dz4 dx. So think of x being replaced with a tuple, one which is dz1 dx and the other which is dz4 dx. Okay, and we'll see how to use this information in just a little bit. Now let's calculate all the derivatives. So we start with dz1 dx, which is simply 2 times x, dz2 dz1, which is simply 5, dz3 dx is e to the power x, dz4 dz3 is 1, dz5 dz4 is negative 1 over z4 squared. And if you don't remember your derivatives, these are very easily available. Go to search Wikipedia for derivatives, and then go to derivatives of simple functions, and you'll see all of these derivatives there. dy dz2 is z5, dy dz5 is z2. Right? And notice I've taken the partial derivative of y because y is dependent on both z2 and z5. dy dx. Right? And how do we do that? Well, let's go through the blue path first. So it's dy dy times dy dz2, it should be dz2, times dz2 dz1 times dz1 dx. So we just take into account the blue portion of x, right? And then we apply the product rule of derivatives, which is simply, so if you don't remember your product rule, derivative of product of two functions is simply the derivative of the sums, right? So it's kind of you keep one constant, you take the derivative of the other, you keep the other constant, you take the derivative of the first one, then you add both of them up. So what we're doing here is we're simply doing the product rule. And now for the green path. So again, it's dy dy times dy dz5 times dz5 dz4 times dz4 dz3 times this should be dz3 dx, right? So you can see that using the back propagation, applying the chain rule and the product rule together becomes a lot more simpler. We just add up all the accumulated gradients. Okay, so now let's start plugging in the values. So dy dy is 1, we know that. Dy dz2, so dy dz2 is simply z5, right? And we'll worry about what z5 is in a bit. dz2 dz1, so dz2 dz1 is simply 5, right? So these are all the substitutions we're doing. And dz1 dx, let's see, dz1 dx is simply 2x, okay. So this is the first part of the equation. Now let's go to the second part. So dy is again just 1. dy dz5, this is z2, okay. We'll worry about what z2 is in a bit. dz5 dz4 is negative 1 divided by dz4 squared, okay. dz4 squared times dz4 dz3 is 1, and dz3 dx, okay, dz3 dx is simply e to the power x, okay. All right, so now let's simplify this a bit. So z5, let's substitute z5 now. z5 is nothing but 1 divided by z4, which is, if I just simplify it all the way through, z5 is simply 1 divided by 1 plus e to the power x, right? z4 is 1 plus z3, z3 is e to the power x. If we substitute all of that, we get z5 equals 1 divided by 1 plus e to the power x. So this is 1 times 1 divided by the power x times 5 times 2x plus z2 is 5 times z1, which is 5x squared, right? So if I kind of substitute z2 all the way through, it's simply 5 times x squared. So 5x squared, and then negative 1 by z4 was, if I substitute z4 all the way through, 1 plus e to the power x, right? So then this is 1 plus e to the power x squared times e to the power x, right? Times 1 times e to the power x. So simplifying this further, we get this as 10x divided by 1 plus e to the power x minus 5x squared times e to the power x divided by 1 plus e to the power x squared. Right, and all the workings in yellow are just to show that this actually does resolve into the derivative of y with respect to x if we were to do it manually using the chain rule and the product rule ourselves. So let's verify that this is indeed true. So we have y equals 5x squared over 1 plus e to the power x, right? And dy dx So let's differentiate the numerator first. So that's 10x over 1 plus e to the power x. And then we keep the numerator as it is and differentiate the denominator. So first that's negative 1 plus e to the power x squared times, just differentiate the part that's inside, which is e to the power x. So this gives us 10x plus over 1 plus e to the power x minus 5x squared times e to the power x divided by 1 plus e to the power x squared. And we see that that's indeed what the backprop algorithm also gave us. Now let's see this entire thing in action in PyTorch. So as usual, we will import torch, define x as a scalar, set the requires grad true, and y is x squared divided by 1 plus e to the power x. As before, PyTorch computed the compute graph behind the scenes. We didn't have to do anything. And in order for it to create the backprop graph, we just call the backward method. And then the gradient of x is 1.7064. Now let's verify that this is indeed true. So I'm going to define another variable dy dx where we'll kind of set the expression manually. So it is 10 times x divided by 1 plus, right? So this is kind of the blue part of the equation, minus 5 times x squared times e to the power x, or divided by 1 plus e to the power x, and this whole thing squared, right? Let's see what that looks like. Sure enough, we get 1.7064. And that concludes the final part of our 3-part series on backpropagation. I hope you enjoyed learning from it as much as I enjoyed making it.